Kubernetes networking, it can feel like a total black box, right? But what if we could follow a single click from a user's browser all the way to your application? Well, in this explainer, that's exactly what we're going to do. Trace a packet's journey step by step.
All right, so let's kick things off with the big question. You've deployed your application, it's humming along in a pod somewhere deep in your cluster. When a user clicks a link, how in the world does that request navigate the complex maze of Kubernetes networking to find the exact correct pod? That's the story we're going to unravel today.
Okay, before we even think about getting traffic from the outside world, we have to start at the absolute foundation. How do pods, the basic building blocks of Kubernetes, even talk to each other? The answer to that is something called the CNI.
So what is this CNI thing? Well, CNI stands for Container Network Interface, and it's basically the magic sauce that gives every single pod its own network identity. Think of it as the low-level plumber of your cluster. It's a standard that says, hey, here's how you connect a container to a network, and then a bunch of different plugins come along and make it happen.
So what does a CNI plugin actually do? Well, it really boils down to three core jobs. First, it creates a virtual network card inside the pod's little isolated network bubble. Second, it slaps a unique IP address on that card from a pool. That's a process called IP address management, or IPAM for short. And finally, it sets up all the necessary network routes so that this new pod knows exactly how to send traffic to any other pod in the cluster, even if it's on a completely different machine.
Now here's where it gets really interesting. CNI isn't just one tool, it's this whole ecosystem of different plugins. As you can see here, you've got options like Flannel, which is great for simplicity, or Calico for really powerful security policies. Then there's Cilium, which is super popular for high performance because it uses this cutting-edge Linux tech called eBPF. The main thing to remember is that your choice of CNI plugin really does have a huge impact on your cluster's capabilities.
All right, so our pods can talk to each other. Awesome. But there's a big problem. Pods aren't permanent. We need a stable, reliable way to find our application. And that brings us to the next layer in our journey, services and DNS. And this is the fundamental problem that Kubernetes services were designed to solve. Pods can be destroyed, they can get restarted on a completely different node with a totally new IP address, or they can be scaled up and down in a flash. If you try to connect directly to a pod's IP, your connection is eventually going to break. So how do you create a reliable, long-lasting endpoint? The answer, of course, is the Kubernetes service. A service acts as a stable, virtual middleman. It gets its very own IP address that, and this is the important part, doesn't change. And it constantly keeps track of all the healthy pods that belong to your app. So when you send traffic to the service, it just automatically forwards it to one of the ready pods. Simple as that.
Now, services come in a few different flavors, but you'll run into three main types. The default is ClusterIP, which is only accessible from inside the cluster, perfect for your internal microservices to chat with each other. Then there's NodePort, which exposes your app on a specific port on every single node in your cluster, which is handy for some basic external access. But for real production traffic from the internet, you're almost always going to use a LoadBalancer service, which actually goes out and creates a load balancer in your cloud provider.
So how does this magic routing actually happen under the hood? Well, there's this little component called kube-proxy that runs on every single node. It's constantly watching the Kubernetes API for new services and pods, and then it programs these low-level Linux networking rules using things like iptables or IPVs to translate that virtual service IP into a real live pod IP. This little guy is really the unsung hero that makes the whole system work. And here's the other half of the puzzle, which honestly makes life so much easier. Instead of having to remember a service's IP address, your applications can just use a simple DNS name. Every service automatically gets a predictable name from the in-cluster DNS server, which is usually core DNS. This makes service-to-service communication incredibly simple and, more importantly, really robust.
Okay, we've got our internal communications sorted. Now let's talk about the final leg of our packet's journey. How do we get traffic from the public internet into our cluster and route it intelligently to the right service? This is where we open the gates with something called Ingress.
So what is an Ingress? At its core, it's basically a set of routing rules just for your web traffic. It operates at layer 7, which means it understands things like HTTP requests. So you can create rules that say things like, if a request comes in for api.example.com, send it to the API service. Or if the URL path is /video, then send it over to the video processing service. It's pretty powerful stuff. Now listen up, because this is a super important point that trips a lot of people up. Creating an Ingress object by itself does absolutely nothing. It's just a piece of paper with instructions on it. You need an Ingress controller, an actual application like Nginx or Traefik running in your cluster to read those instructions and actually make them a reality. The controller is the engine that does all the heavy lifting.
Ingress has been the standard for a long time, and it's powerful for sure. But the community has been cooking up its successor, the Gateway API. It's been designed from the ground up to be way more flexible, expressive, and powerful. Honestly, it represents the future of how we manage traffic in Kubernetes.
And this table here, it does a great job of showing the key differences. Ingress is this one big single resource, and you often have to use all these weird, non-standard annotations to get it to do what you want. The Gateway API breaks this up into different roles, like a gateway for the cluster operator and an HTTP route for the application developer. It also handles both Layer 4 and Layer 7 traffic right out of the box, and has standard ways to do all the cool stuff that used to require those custom annotations.
All right, so we've traced the happy path of a packet, but let's be real. In the real world, things break. So what happens when it all goes wrong? Let's wrap up with some practical, rapid-fire troubleshooting tips for the most common networking failures you're going to see.
Okay, let's start with the classic. Pod A can't reach Pod B. I guarantee you'll hit this one. You've deployed 2 microservices, and for some reason, one just can't talk to the other. Where do you even begin?
Here's your go-to checklist. First things first, just confirm the pods actually have IP addresses. Then, go check the logs of your CNI Plugins daemon set. That's often where the juicy errors are hiding. After that, take a look at the routing table on the node itself. And finally, make sure you don't have a network policy or some external firewall that's actively blocking the traffic.
All right, here's another classic. Your pod seems to be online, you can ping things, but it can't resolve any of your service names. This looks and feels like a network failure, but 9 times out of 10, it's actually a DNS issue.
For DNS issues, your first stop should be inside the pod itself. Check out the /etc/resolve.conf file to see what DNS server it's even trying to talk to. Then, make sure the core DNS pods themselves are actually up and running in the kube system namespace. If they are, check their logs for any obvious errors, and finally, take a peek at the core DNS config map to make sure its configuration hasn't been messed up.
And hey, one last piece of advice, especially for those of you studying for something like the CKA exam. They're going to focus heavily on your ability to debug existing setups. You really need to know how to inspect logs and check connectivity, not necessarily how to do some crazy complex CNI installation from scratch. So, there you have it. We've followed our little packet on its complete journey, from the outside world, through an ingress, to a service, and finally to a specific pod IP assigned by the CNI. But this brings up a whole new question, doesn't it? We've talked about how to connect to these ephemeral pods, but what happens to their data when they disappear? How does Kubernetes handle persistent storage? Well, that sounds like a story for our next explainer. Thanks for joining me.